All right. Let's do some mathematics. Let's see. Problem set up. All right, so today we're going to do some polar coordinate stuff. Let me get rid of that. Let me get rid of this timer here. All right. So, going into this polar coordinate stuff, it's important to just remember some basic things about it. Being that, some key things you're going to use. And oh, there's all kinds of zoomed in. Let's try that again. Some key things you're going to use is r squared equals x squared plus y squared. X equals r cosine theta. Y equals r sine theta. Right, these are going to be sort of the key things we're going to need. But we also have that equation like tangent of theta is y over x. This sometimes comes up. Sometimes it's convenient to use, but it depends on the situation there. Anyway, so we'll start with this and see where we go. All right. So the first example on the problem set here is something relatively straightforward. We just want to find the volume bounded by this paraboloid here and the xy plane, otherwise known as z equals 0. So we're kind of just finding the volume between these two graphs here. Actually, let me go ahead and plot this in Mathematica just so you can see what it is. My drawing's probably going to be pretty bad. All right, well, the capture of Mathematica is way over there. This is good. See if I can't make this big. Let's see. Put this over here for now. That seems pretty good. All right. Okay, good. I caught the mic in time. I actually have a hotkey for my mic now. All right. So just to sort of see what the graph of this looks like, let's plot. So we're doing plot 3D here. Oops, capital D. And since I'm going to graph both of these equations, I need to use the square bracket like this. Right? So this is the paraboloid. 0 is the xy plane. And here I'm going to graph from -3 to 3. And you'll see why. Right? So we get a shape that looks something like this. It's sort of like a dome shape here. Right? So it's got a flat bottom, the rounded top like this, and that's what we're finding the volume of here. So to do this, whenever we're integrating to find like the volume between two things, or if you remember from single variable integrals, the area between two curves, you're just integrating the top minus the bottom each time. All right, so let's go ahead and I didn't turn on my camera. Hello. Maybe. All right. So, so to find this, right, we're just going to integrate the top minus the bottom. Now, actually, one thing I meant to point out back here in Mathematica is look at the region of integration. The region of integration is going to be this circular region here, right? The base of this shape is this disk right here. And if you set the two equations equal to each other, you're going to find out that this is a disk of radius 3. Right? Let's see here. Now back to this. Right, so if we want to figure out what that circle of intersection is, right, we can just set these equal to each other. So plug in z equals 0 here. And we get x squared plus y squared equals 9. So that means the region of integration, sort of the base of this shape here, is the region in the xy plane, which is inside the circle of radius 3, right? Because that solid sits everywhere inside that circle. So the volume here, so actually, let's just sketch this region real quick. Something simple, but so each of these goes out to 3. So we're sort of looking at this region here as the region of integration. All right. So this means that the volume is going to be the double integral over that region. If we write this down in Cartesian coordinates, we end up with this. Let me write dA here. Now, we can probably do this with Cartesian coordinates. But if we do, we're going to have some tricky integrals coming up. For example, I think the second integral, you might get all of it with U substitution. You might have to use trig substitution. But either way, let's make life easier for ourselves. We have polar coordinates. Polar coordinates are exactly created to deal with circular regions like this. So let's use that. All right. So this region R, if I want to redescribe R in terms of polar coordinates, we're looking at something pretty easy. This is what we call a polar rectangle. Right here, all we're saying is R is greater than or equal to 0 and less than or equal to 3. And theta, well, we have the whole circle, so theta goes from 0 to 2 pi. So if we switch this integral to have bounds in polar coordinates, we're going to have just numbers in the bounds, which is nice. Right? So before we set that up, let's look at how the integrand is going to change. Right? So here we have 9 minus x squared minus y squared. Well, if you think about this, this is 9 minus x squared plus y squared like this. So the integrand is really just 9 minus r squared. Now dA, it's important to remember that when we switch dA to polar coordinates, we don't just get dr d theta, right? But because of how converting from the area of a rectangle to the area of like a polar sector works, I don't know if you remember this from the lecture video, but basically you just get this extra factor of an r in there. So we have to have r and then d and d. The r and theta order, you can have one or the other. It's sort of up to you. Typically you're going to do r first. I'd be pretty hard pressed to tell you an example where you're going to use theta first in like a meaningful way. Like here we could do it, but I can't think of one. Maybe with like lines, but I'd have to actually think about that one quite thoroughly. Anyway, so we have dr d theta here, and the nice thing is, again, we switched it to polar, and here's exactly our bounds right here. So r goes from 0 to 3. Theta goes from 0 to 2 pi. And so now we just have to integrate this thing. So you probably want to multiply this out first. So let's integrate this with respect to r. And so we have 9 halves r squared minus 1/4 r to the 4th from 0 to 3 d theta. Let's see here. So we get, let's see, this is going to be 81 halves minus 81 fourths d theta, which is just 81 fourths. And then when I integrate this from 0 to 2 pi, all that's going to turn out to happen is I just multiply by 2 pi. So I'll let you verify that. We've sort of done enough arithmetic on this one. But that's it. Right, so it's hopefully pretty straightforward, this one. Right. So any questions on this one? All right. Excellent. So let's look at problem 2. So here we're kind of doing the same question, but we're asking what's the volume of the region bounded by this upward facing paraboloid here, and the cone z equals 2 minus x squared plus y square root of x squared plus y squared. All right, so this is an upside down cone. It has its vertex up at 2, and then it just opens outward. So let's go ahead and look at this shape in Mathematica again. All right, so I'm just going to change this plot here. So we have x squared plus y squared for a paraboloid, and then we have 2 minus square root of x squared plus y squared. Right. And I won't change the bounds here. All right. So this right here, this is our region. All right, maybe we do want to let's do this. Okay, it actually already had that. All right. So we have the cone here. It doesn't look very coney because it's the aspect ratio is a bit off. So actually, let's put a 1 here. It looks a little better. Right, so again, we have, this is the cone. It looks kind of square shaped just because of how our graph cuts it off. But and see, here's the vertex here. And then you have the paraboloid underneath. So we have this thing with a round bottom and a pointy top here. Right? And if you look at it again, the sort of shadow of this shape in the XY plane is going to be a circle. Right? You cut off all the excess, the shadow is this disk region here. So we need to figure out, well, what is that disk? How big is this? Sorry. Right? So again, let's figure that out by setting these two things equal to each other. So what we can do is figure out, how high they intersect. So we can say take this equation and plug it in down here. So we're going to get z equals 2 minus square root of z. Right? So I just replace the x squared plus y squared with z from here. And what I want to do is I want to try and solve this for z. So we can be a little clever with this. Oops, not that. So we can say z plus square root of z minus 2 equals 0. And we can factor this if we look at this the right way. Right? So think of this as sort of t squared plus t minus 2. Right? And then that would factor as t plus 2, t minus 1. So this will factor, here t corresponds to square root of z. So this is square root of z plus 2, square root of z minus 1. Right? And we're trying to solve this. This one here says square root of z is negative 2, so that never happens. This one here says square root of z equals 1. In other words, z equals 1. So that's the radius, or sorry, that's the height. That's the z value at which these two things intersect. But if we put that back into either of these equations here, we're going to find out that the region R is this region xy, such that, again, if we plug in z equals 1, say, to this equation, we're going to get x squared plus y squared equals 1. And actually, if we plug it in here, we're going to get the same thing as well. So I'll let you sort of think about that. But we're really looking at x squared plus y squared less than or equal to 1 here. So it really is this disk region of radius 1 again. So the volume here, right, it's going to be a double integral over R. Now again, when we're doing the volume of this, we want to integrate the top function minus the bottom function. Oh, I just realized I still have Mathematica up. Sorry. Let me switch back over here. Sorry. I forgot to switch this back over. So let me re-explain real quick what I did here. So what I did is I'm trying to solve here for z, because that's going to be the easier one to solve for. So I took this equation, I replaced over here x squared plus y squared, I replace it with z, and I get this right here. Right? Now what I'm going to do is I'm going to move everything to the left side. And if I look at this carefully, I can actually factor this, right? So to kind of help think about how we would factor this, let's say square root of z is t. Then z is going to be t squared, and minus 2 is minus 2. So we can factor this thing up here into t plus 2 and t minus 1. Since t corresponds to square root of z, that means this here factors as root z plus 2, root z minus 1. And then now we just do our usual, all right, we'll set each factor equal, set each factor equal to 0. This one means square root of z has to be negative 2, which is impossible. This one means square root of z has to be 1, which is possible. Right? So this means the z value at that intersection, the height where those two functions intersect, is z equals 1. And then to figure out, well, what is the shadow of this shape? The intersection is the widest part. So we just need to figure out how wide is that circle, or what's the radius. And if we plug in z equals 1 to either of these equations, we find out it's a circle of radius 1. So that's this right here. All right, sorry about that. So now I actually did want to switch to Mathematica to say, when we're integrating this, right, the paraboloid, the orange one, is actually the bottom shape here. The cone, the blue one, is the top shape. So when we're setting up the integral, we always want to do top minus bottom. So we're going to get 2 minus square root of x squared plus y squared minus the bottom, which is x squared plus y squared, dA. Right? Now again, this is an integral that we can probably do in Cartesian, but it's going to require things like trig substitution and things that might not be fun to do. But that's fine, because we can switch to polar coordinates. And again, this region is really easy to describe in polar coordinates. R goes from 0 to 1. Theta goes from 0 to 2 pi. I'm writing like all of the wrong symbol. Hello. Try this again. 0, theta, 2 pi. There we go. All right. So this volume integral here, we're going to do dr d theta again, just like before. So this will be the theta integral on the outside, the r integral on the inside. Now here, let's look at what this turns into. So we have 2 minus, now remember r squared is x squared plus y squared. So if we have the square root here, that's just 2 minus r. Right? And here, x squared plus y squared, that's minus r squared. Because we have that minus there. dA is r dr d theta. Right? So at this point, the integral isn't very interesting to do. So let's just pop that into Mathematica and compute it real quick. All right. So we're gonna integrate. We're gonna integrate 2 minus r squared times r. We're gonna integrate that. Now remember, the order we type these integrals in, or these bounds in, is looking at our double integral. We type the left one first, then the right one. So 0 to 2 pi. And r goes from 0 to 1. Right? And now we just integrate that. 5 pi over 6. So that means the volume of that shape is 5 pi over 6. Right. And again, as I said before, this is really the more interesting part of this problem. The double integral, it's not terribly interesting at this point. But setting up the integrals, that's by far the most important thing in this problem. All right. Any questions there? All right. Excellent. Let's go ahead and look at problem 3. We're almost to my favorite polar coordinates problem, which is the last one. Literally one of my favorite problems ever. All right. So problem 3, we're trying to find the region beneath z equals xy plus 10 and above the region above the region in the xy plane between the circle x squared plus y squared equals 4 and x squared plus y squared equals 16. Right? So we're looking at this region here. So here we have, some function. And let's look at the region we have here. in the XY plane. Oops. So there's 4. So what we're really looking at here is that region. Oh god, let's try that again. This is the circle of radius 4. And this inner one is the circle of radius 2. Right? So that region we're interested in is this sort of annulus here. Right? So remember how to describe an annulus. Let's call this R. Right? Remember how to describe an annulus. In this case, we're looking at R. Since we have the whole thing, we're just going to directly write this down in terms of R and theta, because polar coordinates will be the best thing for this. Here, the inner radius is 2, so that's as small as it gets. The outer radius is 4. And since we go all the way around, we have our usual theta between 0 and 2 pi. So that's R. And let's look at the graph of this function and see, is there anything special we need to keep an eye out for? So let's plot this. xy plus 10. Since the biggest circle is a circle of radius 4, let's do x goes from minus 4 to 4. Y goes from minus 4 to 4. Now let's look at the graph of this. In fact, let's plot this together with the xy plane, just to see if it ever dips below. Okay. All right, so we do get a little bit of dipping below, but let's see if that actually matters. Right. So to see if that matters, remember, the graph of this, we're only interested in the graph of this orange surface that lies, inside the circle of radius 4. So what we can do is make a cylinder of radius 4. So this one we need contour plot 3D. Right, and I'm going to graph a cylinder of radius 4 to just say, like, all right, everything's got to be inside here. We're going to do x squared plus y squared equals 4. Let's do, so x goes from minus 4 to 4. Oops. That should be a 16. Y goes from minus 4 to 4. And z goes from, I don't know, minus 15 to 15, I guess. Should be good enough. All right, and we're going to use show so we can plot both a plot 3D and a contour plot 3D on the same set of axes. And actually, let's do this. Let's do contour style. Let's make these purple, and let's lower the opacity a little bit. All right. So we're only interested in the part of this graph that's inside the purple cylinder here. Right? And if we look everywhere inside that purple cylinder, this orange sort of saddle here, if you will, it is a hyperbolic paraboloid. It sits above the xy plane, right? Only outside of the cylinder does it dip below, so there's no weird stuff to worry about here. So when we integrate it for the volume, all we have to do is just integrate that function, because it's always the top. It doesn't switch to the bottom at any point. So the volume is going to be the double integral over r of xy plus 10 dA. Right? So now let's switch this over to polar coordinates. So again, we're going to do dr d theta, because that's just usually the most convenient order. Oops. All right, so when I switch this thing to polar coordinates, though, there's no x squared plus y squared anymore to kind of use to switch out. But that's fine, because we know exactly what x and what y is in polar coordinates. This is r cosine theta. This is r sine theta plus 10. R dr d theta. Right? So this is still very doable. Now, if we did this by hand, we would need a u substitution when we did the theta integral. But let's, again, setting up this integral, this part right here is by far the most important thing, because this is the part Mathematica or other computer algebra systems can't do for you. Once you have this, you can just use Mathematica. So let's do that. So we're looking at integrating. And the beautiful thing with Mathematica is we don't even have to simplify this. So r cosine theta, r sine theta plus 10 times r. R goes from 2 to 4. Theta goes from 0 to 2 pi. 2 oi, apparently. All right, and now we just integrate that. Cool, 120 pi. So this is 120 pi. Right, that's all there is to it. Right. Again, I really want to emphasize with these, setting up the integral is by far more important and more interesting than actually computing it at this point. At least for most integrals. Right? So, any questions here? Awesome. Hope you all are doing all right, and I didn't talk to a lot of you yesterday, so I hope you had a good weekend. Doing well with your other classes and such. All right. Let's go ahead and look at the next one here. So the next problem here is we want to set up a double integral giving the area of the region that's outside the circle r equals 2 and inside the circle 4 cosine theta. So this problem actually has two parts, even though I didn't sort of write it like that. So let's say outside r equals 2, inside r equals 4 cosine theta. So this is where it gets a little more interesting with polar coordinates, how to set this up. All of the last three problems, we were integrating over so-called polar rectangles, right? Here, we're really integrating over a polar region, something that's not a polar rectangle. Right? So what does this graph look like? Right, r equals 2 is just a circle of radius 2. So there's no real surprise there. The thing you might, want to remember, this is from like second week of class, actually. So it's been a little while. But, actually, so let me label this one. This is r equals 2. R equals 4 cosine theta is also a circle of radius 2, but it's shifted off of the x-axis. Right, so hopefully that looks somewhat familiar. Right, and of course, you can always use polar plot in Mathematica to check this if you're unsure. So what we're asking for is, let me highlight it. We're asking for the area of this region here. We want the area in here. So this is my region R. So what is the area of that? How do I set this up? So here's where we have to remember how polar coordinates work. Right? So I'll just draw a little diagram over here. Theta measures like this. Right? Theta measures sort of moving in a counterclockwise direction. That's how theta increases. Okay? R increases by sort of moving from the origin out. Right? So R, you should really think of R as sort of emanating from the origin and expanding outward. Right? So what we're going to do to kind of imagine how to set this up is fix a few theta values and see. So when we fix a theta value, we draw a ray going out, right? And then we want to see, like, where does that ray hit first? Where does that ray hit last? If we start here, it hits the blue circle first, and then the green one. We start here, blue circle first, then the green one. Here, blue circle first, then the green. Blue first, then the green. Okay? So what that means is, so the area, right, this is double integral over r of dA. So we do need to switch this to polar. R dr d theta. Right? So what this means is when we're setting up the r integral, the inside bound is the blue curve, just 2. The outside bound, which is the green curve, is 4 cosine theta. Okay. So again, what's important to remember here is it's always sort of inside to outside for R. Okay. Let me just say again, since R sort of starts at the origin and expands outward, the bounds on R are always inside to outside. Inside is the bottom, outside is the top integral. All right. Any questions about that? I know it's a bit of a interesting idea, but hopefully it makes sense. About that? Okay, cool. So now we just have to figure out, well, where does theta start and where does it end? So it's going to start here, because remember, theta moves in a counterclockwise direction. So it starts here and ends here. We need to find the theta values. And the way we do that is we just set these two things equal to each other. Right? So we have r equals 2 and r equals 4 cosine theta. So we're going to get, I'll do it in purple, 2 equals 4 cosine theta. This is saying cosine theta equals 1/2. And we just have to think, well, when is cosine equal to 1/2? Right? What bounds make sense here for that? So here, this one is pi over 3 up here. And then we could say, all right, well, this is 5 pi over 3 down here, but that doesn't make sense for the order of this. So we actually want to use minus pi over 3. The reason we want to do that is because then we're going to start down here at minus pi over 3, and we're going to trace out from here to here. Okay. Oops. So minus pi over 3, pi over 3. Right, so you usually want to choose some sort of smart choice for your bounds here, like this. Right. And that's the area. Right? Any questions about that one? So for problem 2, or for part 2 of this, I'm going to be a little sloppier about putting on the bounds this time. Close enough. Right. So let me just reiterate here. We have, this is theta is pi over 3. This down here is theta equals minus pi over 3. And this time, we're asking for the area inside both of these. We're asking, what is that area? Now, this one actually is a little more interesting. Need to make that better. All right. This one's a little more interesting. Let me draw these purple lines here. Now, here's what I want you to think about. Remember that when we compute the bounds for r, we're always moving from sort of the origin outward. That's how r grows. When we're between these two green lines, we're starting at the origin, and we're always going to the blue curve. Right? It technically, it touches the green curve here, but it's not really bounded below by this green curve. All right? On the other hand, when we get beyond this, there's still some highlighted area here. So here we're starting at the origin, and we're now ending at the green curve in those two regions. So we actually have to split this integral into 3 pieces. This bottom wedge, this middle wedge, and this top wedge. So let me call these R1, R2, and R3 respectively. Okay. Then here, the area, we're going to have to find the area for R1, the area for R2, and the area for R3. Right? We actually have to set all these up separately. Because again, they're bounded by different things. So if we look at R1, it's this region sort of starts at the origin and ends at the green curve, and this stops at minus pi over 3. Oops, sorry. So this one should go to minus pi over 3 for theta. R goes from 0 to 4 cosine theta, because it starts at the origin and ends at the green circle. That's r dr d theta. What is the lower bound on this? So we want to think, well, when is this hitting the origin? Like, where does the circle start coming out? And so you would do that by setting 4 cosine theta equal to 0. And you'll find that the value that makes sense there is actually minus pi over 2. Right? Because minus pi over 2 will make 4 cosine theta equal to 0. And that's sort of, as we move backwards from pi over 3, that's the first place it happens. All right, so that's area 1. Now for area 2, we know this goes from minus pi over 3 to pi over 3. This one starts at the origin and ends on the blue circle. This one goes from 0 to 2. Right? And then we're going to have a similar thing for the last integral. This one starts at pi over 3. The bounds start at the origin and go to the green curve again, and r dr d theta. Right? The upper bound for the outside integral, we have to find out after pi over 3, when does that green circle hit the origin again? Well, it turns out that's going to be at pi over 2. So again, we're just sort of setting 4 cosine theta equal to 0. So that's going to be pi over 2. Right? So that's all there is to that one. Any questions about that? All right. So let's go ahead and do problem 5, and since it's 12:20, I think we'll end on that one, and then we'll take a break and start over. Problem 6 is never going to be on an exam or anything like that. But I think I'll do it at the end of the next session just because it's a really interesting problem. So let's go ahead and do problem 5. So here, we're looking at sort of the, let's see here. We want the area outside r equals square root of 2, and inside r squared equals 4 cosine 2 theta. And we want this in the first and fourth quadrants. Right? So what does this look like? Let's plot this real quick in Mathematica here. So let's see, plot, actually we need polar plot. So here we have square root of 2. And let's see, so we have r squared, so we actually need to write this one in 2 parts. The square root of 4 cosine of 2 theta. Then we also need negative 4 cosine 2 theta. Let's see, let's make r go from 0 to 2. And let's make theta go from 0 to 2, 0 to 2 pi. Oh, sorry, we don't need that. So we're looking at something like this here. All right. So the region we're talking about in this problem is this region on the left here. Oh my god, I forgot to switch over. Right, so this is the graph of these two equations. Right? So that r squared one is obviously the figure 8, the lemniscate there. Square root 2 is the circle of radius square root 2. What we're looking for is, where is the mouse cursor? That's never pointing at the right thing. All right, we're looking for the area in here. Right, this is what we're interested in. Here's the first quadrant, here's the fourth quadrant part. So we want to find that out. So what that means is, well, the outside part here, that's sort of the upper bound for r. The circle is the inner bound for r. So we just need to figure out what is the theta value here and what is the theta value here. So let me sort of try to sketch this real quick. All right, let's pretend that's a good drawing of what we had. So we need, actually, let me use a color that's different. We need to know these two theta values. So to do that, we're going to do the same thing we did before and just sort of set these two equations equal to each other or plug one into the other. So r equals square root 2 is really, r squared equals 2. So plug that into the other one. 2 equals 4 cosine of 2 theta. Right? So this is 1/2 is cosine 2 theta. Right? So for 2 theta, we're looking at stuff like, pi over 3, minus pi over 3 are probably some good choices. Right? Now you might have to, actually for this circle, this is actually all they can be. Right? So if 2 theta is this, that means theta is going to be pi over 6 and minus pi over 6. Right? So it's important to know that 2 theta has to be pi over 3 and minus pi over 3. So here we have pi over 6 on top, minus pi over 6 on the bottom. So the question is, for this green part here, do I use, I need to solve for r. Right? So the area, again, is, our usual dA, integral over r of dA. Theta we've settled. The inside one for r has to be square root of 2. What is the top bound, though? So if we solve this for r, we have, it's either plus or minus 2 square root of cosine 2 theta. Right? It's one of these two. How do we know which one it is? Well, just think, when we plug in pi over 6, do we want a positive r value or a negative r value? Well, when we plug in pi over 6, we want to be in this direction, not in that down here. So we need the positive. And now this is just something you can pop into Mathematica. Right? And the square root of cosine isn't going to be an issue, because you integrate this, you're going to have r squared, and that's going to square it away. So that'll take care of that. So I'll just stick with this as a setup this integral problem. Right. Yeah, so these polar integrals, they can get kind of interesting. Little fun to play around with and just think in a different way about how to set up bounds. So with that, I think, yeah, because there's 2 minutes to the next class. So with that, I think we'll stop there, and I'll hopefully get to problem 6 in the next class. But with that, I'll take a break here for a couple minutes, and see you back here in a few. Sorry about that. Took a second longer than I thought there. Or a couple seconds, but you know. All right. Good to go. All right, cool. So let's go ahead and just get started. So problem 1. Here we're looking at the volume bounded by the paraboloid z equals 9 minus x squared minus y squared, and z equals 0, which is the xy plane. Right? So whenever we're finding the volume between two graphs, what you're doing is you're sort of integrating the top minus the bottom over sort of its shadow in the xy plane. Right? That's sort of the idea here. So what is the shadow? Well, let's go ahead and look at the graph of this real quick. Still, let's see, 9 minus, I wanted to swap this over to Mathematica. Looking at 9 minus x squared minus y squared and 0. We need to make this a bit bigger. Say 3 to 3. Right. So if we look at this region, right, we're looking for the volume bounded by these two things here. By this blue plane here, this is the xy plane, this is z equals 0. And this orange one, that's our paraboloid, 9 minus x squared minus y squared. We're kind of finding the volume of this dome, and the aspect ratio keeps getting changed, but so we can see, this dome is on top, the blue is the floor, and the region that we want to integrate over is the shadow of this in the xy plane. Right? So if you look at it, the shadow of this thing is going to be this circle here. Right? It's going to be that circle and everything inside it. So how do we find what the radius of that circle is? Right? So the shadow is determined by sort of where these two things intersect, right? Where the paraboloid is hitting the xy plane. So all we have to do is come over here and say, well, when does this equation intersect the graph of this equation? Well, to do that, you just plug one equation into the other. So you'd get 0 equals 9 minus x squared minus y squared, right? Because we know z is 0, so we're going to put that in here. All right, and this tells us x squared plus y squared equals 9. So that's sort of the biggest part of the shadow there. And so the region R is going to be your xy values, where x squared plus y squared, right? That shape is sort of everything on the circle of radius 3 and inside. So x squared plus y squared less than or equal to 9. Right? And that's the volume of our region. Or sorry, that's the region that we're going to integrate over. It's kind of like the base of the shape. But again, it's the shadow of the shape in the xy plane. All right. So the volume is going to be a double integral over R of, this was the top function here. So 9 minus x squared minus y squared dA. Right? So that's that integral there is going to give us our bound, our volume. Now the thing here is that we can probably integrate this. We can probably do this. It might require some u substitution, some integration by parts or something like that. This can probably be done in Cartesian coordinates, but it won't be particularly fun. So instead of doing it in Cartesian, we're going to switch this over to, a coordinate system that fits it better. Because this region R, this region R is, let me redraw it down here maybe. Right, it's just a circle of radius 3. Keep getting these really flat parts here. Right, we're just integrating over this. And if we switch this integral to polar coordinates, if we re-describe this region here in polar coordinates, it becomes a lot easier, right? R goes all the way from 0 to 3. Right? And theta is allowed to go all the way around this disk. We're not cut off at any point. So theta is going to go from 0 to 2 pi. So, a disk like this is one of those regions we call a polar rectangle, right? Because it's described in polar coordinates, the bounds are just numbers. Right? So now we just have to swap everything over to polar coordinates. Remember dA turns into R, and then you have your choice of dr d theta or d theta dr. But don't forget about this R right here. Right? That just has to do with sort of how does the area of a rectangle deform when you go to polar coordinates. And when you turn it into this kind of sector thing, it multiplies by a factor of R. Okay, so we have to swap all this stuff to polar now. It's usually going to be the case that you'll do dr d theta. That's usually going to be the better way to set up your bounds. In this particular problem, it doesn't matter. But there's not that many cases where you'd want to do theta first. Not very many. It's not impossible, but typically you're not going to have polar equations given as, theta equals some function of r. Again, it's not impossible, but not something you're typically going to see. So if we do dr first, that means the inner integral is 0 to 3, the outer integral is 0 to 2 pi. Now, the integrand here, let me say we can rewrite this like this, 9 minus parentheses x squared plus y squared. And if you remember, in polar coordinates, r squared is x squared plus y squared. So that integrand just comes down as 9 minus r squared. Right. And at this point, it's just a typical integral. You can distribute that r and do the usual business. Let's go ahead and use Mathematica to compute it. Because as I was saying, sort of this part here, setting up this double integral, that's something a computer program typically can't do for you. Mathematica can't do. But at this point, now it's just Calc 1 again, doing a simple integral. So we don't really need to worry about that so much. So let's integrate this. We have 9 minus r squared times r, 0 to 2 pi for theta, and 0 to 3 for r. All right, so the important thing to remember about integrate is the first set of bounds is for your very outside integral, the very left integral. The next set of bounds is for the next integral to the right. So you list your bounds in the same order you list your integrals. Right? So, all right, 81 pi over 2. So again, the actual computation isn't incredibly interesting. But do feel free to, double check that you remember how to do it if you want. Any questions about this one? Get back over here. Hopefully that one was pretty straightforward. All right. Cool. All right, so let's go ahead and look at the next problem. Problem 2. So in problem 2, we want the region bounded by the paraboloid, z equals x squared plus y squared, and the cone, z equals 2 minus square root of x squared plus y squared. All right. So we want to find the volume of the region between these two curves. Okay. So I'm going to hop back over to Mathematica here so we can graph this. 2 minus square root x squared. Whoa, what happened there? Plus y squared. All right, so let's go ahead and switch back over. If we plot that, we're going to get a shape that looks something like this. Actually, that disk is quite a bit smaller, so let's zoom in on that a bit. All right. So we have, in the shape that's actually bounded by these, we have that cone on top, or sorry, I don't know why it captures the cursor in the wrong spot. It has the cone on top here, and it has the paraboloid on bottom here. So that's really the only part we have to care about in this. And then when we're setting up the bounds, when we're trying to find the region of integration, what we want to do is say, all right, looking at this from the top down, what is the shadow that this shape makes? Well, the shadow it's going to make is the circle that these two intersect at, and then everything inside it. So it's going to be some kind of a disk. Question is, well, what is the radius of that disk then? You might be able to tell here it kind of looks like the radius is going to be 1, but we should verify that. Right? The way we verify that is, well, we find out where they intersect at, and then from there we can see, well, what is the radius of that intersection? So how do we do that? Well, we need to do basically what we always do to try and see where two functions intersect, is we plug one into the other, set them equal, something like that. And what we're going to do here is, here I have an x squared plus y squared. Here I have an x squared plus y squared. So to make my life easier, what we're actually going to do is figure out, well, what height do they intersect at? Because once I find the height, the z value, I can just use this first equation, plug the z value in, and then I immediately know what the radius is. In fact, the radius is equal to the square root of the height. You can tell from here. So let's do that. So we're going to plug z in under here, and we get z equals 2 minus square root of z. Now we have, sorry, that's a z, not a 2. Right? So we need to solve this for z. Now that might look a bit complicated, but I promise you it's actually not that bad. So let's start by moving everything to one side here. Right? So I need to solve this for z. Now, I claim you actually know how to do this. You just might not be used to looking at it this way. So this equation right here is a quadratic equation, if you think about it in the right way. I'm going to replace square root of z with t, and then z, if t is square root of z, then z is t squared. Right? And to factor that, I get t plus 2, t minus 1. So what that means is when I swap t back for square root of z, this becomes square root of z plus 2, square root of z minus 1. Right? So you can do all these kind of neat tricks if you just sort of think of, the algebra in clever ways. And now we can start solving for z. So here, we just set each factor equal to 0. This says square root of z has to be negative 2. This one says square root of z has to be 1. Okay. If we look at this doesn't have a solution, right? The square root can never be negative, so that's gone. This one here tells me that z has to be 1. Right? So now I know what height they intersect at. And so then I also know, by taking this equation here and plugging it in for that z value, I know that the disk that they intersect in is radius 1. It's x squared plus y squared equals 1. That's going to be its shadow in the xy plane. So our region R in this problem is a disk of radius 1. Now, when we're finding that's not what I wanted, right? When we're finding the volume here, we're going to integrate over R. We want to integrate when we're finding the volume between two graphs. It's going to be just like finding the area between two functions. You take the top part and you subtract the bottom part, and that gives you the height. Top minus bottom is height. So if you remember, the cone was on top here. So 2 minus x squared plus y squared. That's the top part. And then minus the bottom, which is just the paraboloid. dA. So that's the volume integral we're looking at. Now again, this one, we can again probably still do this by hand, keeping it in Cartesian coordinates. But we'd have to do things like u sub, integration by parts, probably some trigonometric substitutions. And honestly, that wouldn't be very fun. So let's switch this to polar coordinates. Because again, we have a nice circular region. The region of integration is very nice in polar coordinates. It's just a disk. So it's an r theta. R is between 0 and 1. Theta is between 0 and 2 pi. Right, so it's a nice, simple region again. So the bounds, we already know even. 0 to 2 pi, 0 to 1. Right? Remember, dA is going to turn into r dr d theta, but let's change this piece by piece. So here we have a 2 minus square root of x squared plus y squared. That's square root of r squared, so this is just r. Minus x squared plus y squared is r squared. And then r dr d theta. Right? And so we can, you can multiply this out and compute it by hand if you want. We'll do it here with Mathematica because, again, the most interesting part of this problem is setting up this integral. Once you have that, then it's just computation. So let's swap over here. So what we're integrating here, see here, we want to integrate 2 minus r squared. Oh my god, please. Right? Times r. And again, the nice thing with Mathematica is I don't have to distribute this and simplify, just toss it in there as it is. And my bounds, again, the first set here, this set is for the first integral, counting from the left. This one is for the second integral, counting from the left. And run that. All right, we get 5 pi over 6. So this integral is equal to 5 pi over 6. Right. So again, it's not very, I think at this point, not very enlightening to do all the just compute integrals, right? You guys did lots of this in 135 or whenever you learned integration. You did lots of integrals. So I'm not so concerned with sort of doing those so much as setting up these integrals. All right. So that's it for number 2. Any questions about this one at all? Awesome. Yeah, so hopefully this isn't too bad so far. Now we're going to look at one that's a little more interesting. Please, thank you. Sometimes it just refuses to write. All right. So problem 3 here, we want to find the volume that's below z equals xy plus 10. So below that region and above the region bounded by, or the region, I should say, in the xy plane between x squared plus y squared equals 4 and x squared plus y squared equals 16. So this region between two circles, this is what we call an annulus. So the region between these two functions is what we would call an annular region. Again, it's between two annuli. Anyway, so, sorry. All right. So what's, how do we do this? Well, first what we want to do is, let's look at what this region is. So let me pull this up here. Right. So we're looking at this region right here. Right. So here's xy plus 10. This is that orange curve, which I swear, I wish it would capture my mouse cursor where it actually is. Let's see where, okay. So this orange thing here, this is xy plus 10. So we want the region that's sort of beneath this blue plane here. This is the xy plane. So we want the part of this orange thing that's above that annulus. Now, if this orange part was always above the xy plane, it would be very easy to say that this is always sort of the roof of the shape in some sense. But we need to make sure of that it's at least always on top in the region we're interested in. Right? So to do that, what I'm going to add in is a cylinder of radius 4. That's sort of like the outer edge of that annulus. So this would be like the outside wall, if you will, of the 3D shape. And as long as this orange graph always stays on top inside that, then we're good to go. We don't have to worry about the top and the bottom switching sides. So I'm going to add that stuff in. Right, so this is going to plot a cylinder of radius 4, and it's going to make it purple and make it a little bit see-through. Okay. So let's go ahead and plot that, and we get this shape here. So if you look at it, everywhere inside this purple cylinder, that orange, sort of what's called a hyperbolic paraboloid, that orange thing is on top all the time here, which is great. So when I'm trying to find the volume of this and you do top minus bottom, it's always going to be, xy plus 10 minus 0, because the bottom is always the xy plane here, right? Which is wonderful. So let's get to setting up our integral. Right? So if we're looking for a region R that's between these two, we're sort of saying, all right, well, the region is xy, where this is the inside circle, so x squared plus y squared has to actually be bigger than that, but it has to be inside this circle, so it has to be less than or equal to 16. So that's our region R. How do we re-describe this in polar coordinates? So if r squared, so this right here, this is r squared. If r squared has to be greater than or equal to 4, then r has to be greater than or equal to 2. If r squared is less than or equal to 16, r is less than or equal to 4. And if you remember that shape we had, we have the whole annulus. We have all 360 degrees of it. So theta goes from 0 to 2 pi. Right? There's no restriction. Right? So the volume here is going to be a double integral over that region of xy plus 10 dA. Oh, this is problem 3. Oh, 3 there. Okay. So we want to integrate this shape. When we integrate this, though, we need to switch the shape to polar coordinates, or this integral to polar coordinates. Sorry, words are hard. So we need to do our usual business here. So, theta will be the first one, 0 to 2 pi. R will be the second one, 2 to 4. Now this xy plus 10, there's no x squared plus y squared anymore to immediately switch. But this is fine, because we know that x is r cosine theta, y is r sine theta. So we can always, if we don't have, x squared plus y squared or that kind of form to use, we can, just swap out each x and each y individually for these. Right, so this will be r cosine theta, r sine theta, plus 10. And then dA turns into r dr d theta. Okay. And then we need to integrate that thing there. So to integrate that, as usual here, if you want to do this by hand, let me just say what would happen is to deal with that sine times cosine, that's just a u substitution. And then the rest of it is straightforward. So let's go to Mathematica to compute this, though, which I actually already have right here. So we're integrating, r cosine theta times r sine theta plus 10 times r. I listed these in the wrong order. It doesn't actually matter in this case, but it doesn't matter in this case because the bounds are all numerical, so you can swap the order if you want. But anyway, So you'll run this integral and you're going to get 120 pi. So that means the volume of that shape is 120 pi. Again, setting up the integral is a lot more interesting than actually computing it. So that's the part I would worry about more, is setting up the integral correctly. All right. So any questions about that at all? All right, cool. So let's go to problem 4 here. Oops. Problem 4 actually has 2 parts to it. Right. So in problem 4, we want to, in part 1, we want to find the area outside the circle r equals 2 and inside the circle r equals 4 cosine theta. So, graphing these kinds of things, it's been a minute since we've done it. I think it's back in January. It's the second week of class we talked about graphing polar equations. It might be a little while. But let me toss the graph of these out real quick. At 1, 2, 1, 2, 2, 2, 3, 4. All right. So the graph of this, I'm going to do this one in blue, this one in green. All right, r equals 2 is an easy one. That's just a circle of radius 2. Radius 2 is bad. All right, so nothing terribly special there. Now, if you remember, for cosine theta, if you have something that's a number times cosine theta, that's a circle of radius half this number that goes from the origin out to that number. So in this case, sort of the compass points of this circle are right here. And we have that. So here we have r equals 2 is this one. R equals 4 cosine theta is this one. And so the area we're trying to find here is this stuff right here. We're trying to find the area of that region right there. That's outside the circle of radius 2, but inside this other circle of radius 2, 4 cosine theta. Right? So when we're trying to set up bounds for an integral like this, so I guess let me say real quick, let's call this region R. The area, change, the area here is still double integral of R dA. Right, so this doesn't change. Right, so here we need to figure out some theta values, some R values, and then we have R dr d theta. Again, doing the R integral first is going to make more sense here. So how do we set up these bounds? Right, so when we're looking at R, the important thing to remember with R when we're graphing polar equations, is R starts at the origin and expands outward. Right? That's the important thing to remember about polar coordinates. Right? In fact, let me there's a picture I can draw here. So theta, theta measures like this. It measures in the counterclockwise direction. No matter where r is, for any theta value, r measures outward, measures radially outward. Right, so we're always going inside out. So here, r starts at the origin. Let's say we go out along whatever angle this is. It hits the blue curve first, and then the green one. Here, it's going to hit blue first, then green. Start here, blue, then green. Blue, then green. Right? So since it's always hitting the blue first and then the green, that means the bounds are going to be the blue equation for r, which is 2, and then the green equation for r, which is 4 cosine theta. All right? Then the question becomes, well, what are the bounds on theta? This is usually the trickier part. So let's think of this shape moving in the counterclockwise direction. It sort of starts here at whatever theta value this is, right, where the blue and the green intersect, and it ends up here at whatever value these intersect at. Does that make sense? Again, since theta moves in a counterclockwise direction, we want to look at our shape and we want to start sort of at the bottom part, and we want to make sure we move counterclockwise through that shape. Okay? So to move counterclockwise through it, we start at the bottom, go to the top. Hopefully that makes sense. Right? So we need to figure out what's a good theta value here, what's a good theta value there. Well, this is where the two graphs intersect at, so we're going to do what we always do to find where two graphs intersect. We set the two equations equal to each other, or plug one into the other. So here we have r equals 2, r equals 4 cosine theta. So we have 2 equals 4 cosine theta, which means that cosine theta has to be 1/2. And let's look at some theta values for this. Right? Well, right, so cosine of theta equals 1/2 at pi over 3. This up here looks an awful lot like pi over 3. So we'll use that. Now, another value is 5 pi over 3, and that matches up with this here. But 5 pi over 3 is a little bit problematic to use. Because if we integrate from 5 pi over 3 on the bottom to pi over 3 on the top, as far as the calculus goes, that's going to move in the clockwise direction, because it's going from a bigger number to a smaller number. So what we have to do, since we sort of want to end at pi over 3 on top in this integral, that's sort of like going in the counterclockwise direction, that's kind of the end of the shape, we need to come up with another angle that gives us the same spot right here, but is below pi over 3. Can you think of what a good choice for that might be? I'll give you the hint that it somehow has to be equivalent to 5 pi over 3, because we do have to be in the same spot here. Yeah, negative pi over 3, exactly. So negative pi over 3. Because again, that we want to make sure we start at a lower number and end at a higher number. And, we can always do that. That's the nice thing about, trig functions is they're periodic. So there's lots of ways to get a theta value for the same spot. Keep minus pi over 2 in mind for the next part. It's this one we needed minus pi over 3. All right. Okay. So let's look at All right, so that's setting up the integral for the area of this one. All right. Any questions about this one at all? Hopefully this makes sense. All right. So let's do the next one, which is part 2 of this is inside both circles. All right. So I'm going to do just a rough sketch of these. The blue one was the circle. And that circle looks bigger and lopsided. I'm really bad at getting nice circles on this. Anyway, doesn't matter. Right? So the region we're looking for the area of is this stuff in here now. Now this does get a bit trickier this time. I want to think about, what's the inside and what's the outside here. So, we're always going to start at the origin and move our way out. So here we start at 0, end at the blue. Here we're starting at 0, ending at the blue. But if I take a really steep angle, I'm actually ending on the green curve there and going down, I actually end on the green curve there as well. So I'm always starting at 0. I'm always starting at the origin, even though the green curve does go through the origin. Here we're sort of measuring, we're always starting at 0 and going outward. So, all right, so there's kind of, a part down here that starts at 0, ends on green, then it switches to ending on blue, then it switches back to ending on green. And those places where it switches are the same theta values we found earlier. Right? So we kind of have 3 regions here, if you think about it. This one is, I'll call it R2. Down here, this one's R1. This one's R3. So if we wanted to find that area, we actually have to break this into 3 parts because the R values, they all start at 0. Sometimes they end at green, sometimes they end at blue. And that changes, that's kind of in 3 distinct parts there. So the area of this, I'm going to have to integrate this over the 3 parts separately. So for R1, so these are all going to be R, dr, d thetas. Right. For R1, that's this little sliver down here. It starts at 0 and it goes to the green curve, which was 4 cosine theta. In fact, the R always starts at 0 for all of these. Right? The question is, what does the theta do? Well, if we look at this, it sort of, as we're moving in the clockwise or counterclockwise direction, kind of has to end at minus pi over 3. So where does sort of this circle in some sense start at? What theta value does this circle move away from the origin and start moving toward minus pi over 3, toward this purple line here? What theta value would that be? Yeah, so that's the minus pi over 2 right there. Right, so minus pi over 2 is when this starts coming out of the origin. Here we have minus pi over 2. Right, so that takes care of the first part. The second part, this is the part that starts at 0 and ends on the blue circle. Blue circle is radius 2, so r goes from 0 to 2 there. And here, this is the part of the circle between these two purple rays here, between these two theta values. So this one's minus pi over 3 to pi over 3. Right? And then finally, this last one, this starts at the origin and ends on the green curve again. So 4 cosine theta. All really squished in there. Right? And then the theta values there, as we move in the counterclockwise direction, you can see sort of it's going to start at pi over 3 this time. And we need to keep going until this touches down back at the origin. So the way you would solve for this algebraically, of course, is to take 4 cosine of theta and set it equal to 0, because that's when it actually hits the origin. So if you wanted to do it algebraically, you're looking at 4 cosine theta equals 0. And that's another way to see the minus pi over 2 down here. And it's the same way you would see the analogous pi over 2 up top. So pretty interesting, I think, how you set this up here. Right. So any questions about that one at all? I know this one gets a little more complicated than the last one. And again, it all comes down to sort of looking at how you measure r. R, again, always goes from the origin outward. So it's sort of the bounds on r. So if you think of the bounds for x, we were saying left to right. The bounds for y were bottom to top. For r, it's sort of inside to outside. Theta is a little trickier to describe. It's sort of like, where do you start and where do you end a rotation? It doesn't have a nice kind of like inside outside, left right kind of deal. But theta is always just, as you view your shape in the counterclockwise direction, where does it start, where does it end? All right. So we are at 124. So if you do have other classes or commitments you have to do, feel free to hop out if you want. I'm going to go ahead and finish the last 2 problems, though, just so, if you ever look back at the video, you can see what's going on with them. Or if you want to stick around. All right, so let's look at number 5. Problem 5 is probably the most interesting one on here, in terms of polar integration. So here, we're looking at the area between r equals square root of 2 and r squared equals 4 cosine of 2 theta in the first and fourth quadrant. In other words, sort of on the right half of the plane, what that means. Right? So we want to look at, well, what does the graph of this region look like? Right? What is going on in this problem? So let's switch back over to Mathematica so we can see the shape. I have it plotted right here. Okay, so this thing right here, this is the blue one, is the graph of square root of 2. This green one here, actually, I'm going to check something real quick. If I take that out, oh, Okay. Turns out I didn't need that. But I like green better than orange, so let's keep that color. This green one here, this is the graph of r squared equals 4 cosine 2 theta. Right? So what we're asking for when we say the area between these two in the first and fourth quadrant, we're talking about this region right here. This little crescent moon shaped thing right here. Right? Because actually I didn't write it on the tablet here, but it says outside of the circle r equals square root 2, and inside this what's called a lemniscate, which is this figure 8 thing. Right, so outside the blue one, inside the green means this kind of half or crescent moon shape here. Right? So I'm gonna redraw this real quick. Not too terribly. All right, let's come back over here. An attempt was made at drawing this. So we're interested in this area right here. All right, we're interested in that area. So, if we let's call this r again. Right? So we're trying to compute this double integral over r of dA. So we need to come up with some theta values, some r values, and we have r dr d theta. So if we look at this, the lower bound on r should be fairly simple to figure out, right? We start at the blue, end at the green. So it should go from square root of 2, to whatever the upper half of this is, right? So actually, when we solve this for r, we're kind of asking like, we get this kind of thing going on here. So we need to figure out what theta values we're going to use before we start saying, okay, pick the positive or the negative square root. Right? We need to settle on theta first. Now, there's actually only one choice we can really use here, but is that true? Maybe that's not true. Ignore that statement. Anyway, let's see here. So we need to figure out what these theta values are here and here, right, where these things intersect at. So to do that, just as always, we're going to plug one of these into the other. So if we plug this in here, we're going to get 2 equals 4 cosine of 2 theta, which says that cosine of 2 theta is 1/2. So we have a similar sort of situation as before, right? But this time it's 2 theta because the inside of the cosine is 2 theta. So 2 theta is pi over 3 minus pi over 3. Right? And so that means theta is going to be pi over 6 minus pi over 6. So this should be pi over 6 here. This should be minus pi over 6. Right? And so pop those in for the bounds here. Minus pi over 6 to pi over 6. Right? So in that case, between here, we then want r to be a positive value for the green curve, right? If we had used theta values on this side, right, we would need negative r values to get back over here. But we're using theta values between these two, so we need r to be positive, which means we want the positive square root here. Right, remember, negative r, like if I had, this here would be 4 pi over 6. No, 5 pi over 6 would be this intersection. If I used a negative r, that would put me down here somewhere. Anyway, so this is the integral. Now you could compute this by hand. This would actually be doable by hand despite the square root of cosine thing there. But not terribly worried about that. Again, the most interesting part of this is setting up the bounds. So on that part, is there any question? All right, cool. So I know these polar integrals can be a little bit tricky sometimes, setting up the bounds, but really all you have to do is just sort of think of how polar coordinates work. R goes from inside out, theta goes in a counterclockwise direction. So you just have to you just have to sort of try and think of your function in that way. You'll be good to go. All right. So problem 6, I want to do this one just because I think this is a really neat problem. Because it really shows off how polar coordinates can really take an integral that's like impossible Cartesian coordinates and turn it into something pretty simple. So what we're asking in this function is we're trying to show that the standard normal distribution, if we sort of integrate all of the possibilities for this, we should have probability 1 of hitting something on the number line. So what we're sort of doing is we're trying to compute this integral here. Right? This would give you the total probability, and this should be 1 if it's a good probability distribution. This is 1 over square root 2 pi e to the minus 1/2 x squared dx. So, try as you might, even ignoring the bounds there, there's no way to do this integral, right? This x squared in here, and there being no x out here, there's nothing we can do. We're sort of stuck with this. But there's a neat trick we can do with multivariable. All right. So what I'm going to do is say, all right, well, I want to compute this integral. I'm going to just use phi for the moment. I want to compute this integral, but this is hard. So let me square this. Right? So this says essentially that I'm integrating this function twice and multiplying it together. Right? All right, cool. The variable in here doesn't matter. So let me change one of the variables. Right? That doesn't change anything, right? This is just a dummy variable. I've not really done anything spectacular here. All right, but now, since these two variables don't have anything to do with each other, I can combine it together into one integral, into one double integral. Right? Oops, that should say dx dy. Right? I can just combine this together. Because if you think about it, like, when I do this double integral, these integrals sort of happen separately anyway. Like I can factor out the phi y here. So there's no difference here. All right, so now let's go ahead and multiply those two functions together. All right, so I'm going to replace them with what they actually are now. All right. And if we simplify this a bit, we're going to have this. Right? So if you look at this, we're actually getting somewhere now. Right? This might be something we can deal with. Because we have a nice x squared plus y squared, which, you know, dx dy is going to turn into r dr d theta, so we can set up a u substitution. So we want to switch this to polar coordinates. So it turns into this. Now the question is, what are the bounds here? So each of these go from minus infinity to infinity. So we're integrating over all real numbers for x and all real numbers for y. So we're trying to describe the entire xy plane here. So if you think of, think about how could you possibly express the entire xy plane in polar coordinates? What would you need as bounds for r and theta to do that? Think about that for a second. So if you think about the entire xy plane, you can revolve all the way around it. So theta should probably go from 0 to 2 pi. If you think about what r has to be, right? R, remember, r measures from the origin outward. So if we're trying to get the entire xy plane, we want to measure from the origin all the way to infinity. So not only does polar coordinates make the integrand doable, it also gets rid of 3 of the 4 infinities that we had, which is pretty nice. So if we integrate this, we need to integrate this with respect to r first. So let's see. If we integrate this, we get negative e to the 1/2 r squared. Is that right? Yep, that should be good. From 0 to infinity, d theta. Right? So in order to do this bound with an infinity in it, remember we need to really do that as a limit. We have like limit as r goes to infinity of, don't do that, negative e to the 1, I lost my negative there, 1/2 r squared, right? And then minus, plug in 0, we're going to get negative 1. Right? Now, if you look at this limit here, we have e getting to a larger and larger and larger negative power. So this is actually 0 plus 1. And I'll let you finish it off from here, but you're going to have 1 over 2 pi times 2 pi, which is going to be 1. So what we've shown is that the integral that we wanted squared is 1. Since this function here, this function is always a positive number, when we square root this, we have to take the positive square root. And so the integral of the standard normal distribution is 1. So even if you use a different normal distribution that has, say, a standard deviation that's not 1, or a mean that's not 0, in other words, so the graph of this is that bell curve, that famous bell curve. And sort of the standard deviation says how kind of like sharp that bump is in some sense. And the mean is sort of like the middle of the area. So no matter where that middle is, no matter how kind of sharp that bump is, that area underneath it should always be 1. Because you're kind of saying, like, if you add up all the possibilities, which is the area underneath the curve, something should always happen. There should be a probability 1 or 100%. Something. Right? And that's what this is saying here. Yeah, so I find this one personally to be just a really interesting application of polar coordinates. Like I said, I don't think I've said it in this half. There's not going to be any mandatory stuff that you have to do an integral like this. I just think it's a really important function and a really neat trick to show off how to actually integrate such an important function. But on that note, any questions before we end for today? All right. On that note, then, have a good afternoon, and I'll see you tomorrow for some triple integrals.